Identifying tantalum capacitors and how it work in electronics. Tantalum polymer capacitors, also known as solid tantalum polymer capacitors or conductive polymer tantalum capacitors, are a type of electrolytic capacitor that combines the advantages of tantalum technology with conductive polymer materials. Here are some key points about tantalum polymer capacitors. Tantalum polymer capacitors have a specific construction that distinguishes them from other types of capacitors. Here is an overview of their construction. Tantalum anode. The capacitor's anode is made of tantalum, a metal known for its high capacitance per volume and excellent stability. The tantalum anode is formed as a porous structure, which increases the surface area and allows for more effective electrochemical reactions during the capacitor's operation. Conductive polymer cathode. Instead of the traditional manganese dioxide, MnO2, electrolyte used in conventional tantalum capacitors, tantalum polymer capacitors use a conductive polymer material as the cathode. The conductive polymer replaces the solid electrolyte, resulting in lower equivalence series resistance (ESR) and equivalence series inductance (ESL) compared to traditional tantalum capacitors. Solid electrolyte. Tantalum polymer capacitors have a solid electrolyte, which is typically a polymer-based material. The solid electrolyte provides stability, low ESR, and good temperature characteristics. It also contributes to the enhanced capacitance stability of tantalum polymer capacitors. Cathode plate. The conductive polymer cathode material is applied as a thin layer onto a metal plate, which acts as the cathode terminal. The cathode plate is positioned within the capacitor structure, adjacent to the tantalum anode. Encapsulation. Tantalum polymer capacitors are encapsulated in a protective casing to provide insulation and mechanical support. The casing is typically made of epoxy or other suitable materials. The encapsulation helps protect the internal components of the capacitor and provide stability in various environmental conditions. Markings in terminals. Tantalum polymer capacitors have markings on their casings to indicate important information such as capacitance value, voltage rating, tolerance, and polarity. The terminals of tantalum polymer capacitors are usually metal leads or surface mount pads, allowing for easy connection within electronic circuits. The construction of tantalum polymer capacitors combines the advantages of tantalum technology, including high capacitance per volume and stability, with the benefits of conductive polymer materials, such as low ESR and enhanced high-frequency performance. The specific construction and materials used in tantalum polymer capacitors contribute to their performance characteristics, reliability, and suitability for various applications. The conductive polymer material used in tantalum polymer capacitors serves as the cathode in the capacitor construction. It replaces the traditional manganese dioxide, MnO2, electrolyte found in conventional tantalum capacitors. Here are some key points about the conductive polymer material in tantalum polymer capacitors. Purpose. The conductive polymer material is responsible for providing the necessary electrical conductivity and ion mobility within the capacitor. It enables the flow of current during the charging and discharging processes. Lower ESR. One of the primary advantages of the conductive polymer material is its significantly lower equivalent series resistance, ESR, compared to traditional tantalum capacitors. Low ESR allows for more efficient energy transfer, reduces power losses, and improves the capacitor's high-frequency performance. Enhanced frequency response. The conductive polymer material contributes to improved high-frequency characteristics of tantalum polymer capacitors. Its lower ESR and equivalence series inductance, ESL, enable the capacitor to handle high-frequency signals with minimal signal distortion and attenuation. Stability. The conductive polymer material enhances the stability of tantalum polymer capacitors. It helps maintain the capacitor's electrical properties over a wide range of operating conditions, including temperature variations. This stability ensures consistent performance and reliable operation. Conductivity mechanism. Conductive polymers used in tantalum polymer capacitors typically consist of long chains of organic molecules with conjugated double bonds. These conjugated double bonds allow for the delocalization of electrons, resulting in electrical conductivity. Polymer types. Various conductive polymers can be used in tantalum polymer capacitors, including polythiophene, polypyrrole, and polyaniline. Each polymer type has its own characteristics, such as conductivity, stability, and compatibility with other capacitor components. The specific conductive polymer material used may vary depending on the manufacturer and the desired performance of the capacitor. Compatibility with solid electrolyte. The conductive polymer material must be compatible with the solid electrolyte used in tantalum polymer capacitors. The combination of the conductive polymer material and the solid electrolyte ensures stable and reliable capacitor operation. The conductive polymer material in tantalum polymer capacitors plays a critical role in their improved electrical performance, lower ESR, and enhanced frequency response. It contributes to the capacitor's stability, high-frequency characteristics, and efficiency in various applications where low ESR and high-quality signal processing are required. Low equivalent series resistance, ESR, is a desirable characteristic in capacitors, particularly in applications where efficient energy transfer, high-frequency performance, and low power losses are important. Here are some key points about low ESR in capacitors. Definition: ESR refers to the total resistance of a capacitor as seen from an external circuit. It represents the combination of the internal resistance of the capacitor, the resistance of the electrode materials, and the resistance of the dielectric material. Low ESR indicates lower energy losses within the capacitor during charging and discharging. Efficient energy transfer. Capacitors with low ESR allow for more efficient energy transfer between the capacitor and the connected circuit. Low ESR enables faster charging and discharging times, reducing power losses and increasing the overall energy efficiency of the system. High-frequency performance. Low ESR capacitors are crucial in high-frequency applications where rapid charge and discharge cycles occur. They minimize energy losses, maintain signal integrity, and reduce signal distortions at high frequencies. Low ESR allows capacitors to effectively couple, filter, and decouple high-frequency components without significant attenuation or phase shifts. Ripple current handling. Capacitors with low ESR can handle higher ripple currents effectively. Ripple current is the AC component superimposed on the DC voltage in power supply applications. Low ESR capacitors minimize energy losses due to the current flowing through the internal resistance, reducing self-heating and improving overall capacitor reliability. Power dissipation. Low ESR reduces power dissipation within the capacitor, resulting in lower heat generation. Capacitors with low ESR operate at cooler temperatures, contributing to improved reliability and lifespan. They are particularly beneficial in applications where temperature rise must be minimized, such as in power electronics or environments with limited cooling options. Voltage stability. Low ESR capacitors help maintain the specified capacitance value under different applied voltages. They exhibit minimal changes in capacitance with voltage variations, ensuring stable performance and accurate voltage regulation in voltage-sensitive applications. Material selection. The choice of capacitor type and dielectric material significantly influences the ESR. Certain capacitor types, such as tantalum polymer capacitors and aluminum electrolytic capacitors, are known for their low ESR characteristics. The use of conductive polymer materials or specialized electrode configurations helps achieve low ESR in these capacitors. Low ESR is particularly important in applications such as power supplies, decoupling circuits, filtering circuits, audio amplifiers, high-speed digital circuits, and other circuits that require efficient energy transfer, high-frequency response, and low power losses. When selecting capacitors with low ESR, it is crucial to consider the specific ESR requirements, voltage rating, capacitance value, temperature stability, and other performance factors that are relevant to the application. High capacitance refers to the ability of a capacitor to store a large amount of electrical charge per unit voltage. Capacitance is a fundamental property of capacitors and is measured in farads, F. Here are some key points about high capacitance in capacitors. Definition: capacitance is a measure of a capacitor's ability to store electrical charge. High capacitance means that a capacitor can store a larger amount of charge for a given voltage compared to capacitors with lower capacitance values. Importance: high capacitance is desirable in various applications where the storage of large amounts of electrical charge is required. Capacitors with high capacitance can deliver more energy, provide longer discharge times, and support higher currents. Energy storage: capacitors with high capacitance can store more energy, making them useful in energy storage applications. They can store energy for later release, provide power during peak demand, and smooth out voltage fluctuations. Filtering and decoupling: high capacitance capacitors are often used in filtering and decoupling circuits. They can effectively filter out unwanted noise or ripple components in power supplies, improve power quality, and stabilize voltage levels. Time constants: capacitance determines the time constant of a circuit, which affects the charging and discharging rates. Higher capacitance values result in longer time constants, leading to slower charge and discharge times. Space considerations: high capacitance capacitors are particularly beneficial in applications where space is limited. They allow for higher energy storage in smaller physical packages, enabling miniaturization and space optimization in electronic designs. Voltage ratings: it is important to consider the voltage rating of high capacitance capacitors to ensure they can handle the applied voltage without experiencing breakdown or failure. Higher voltage ratings are typically associated with capacitors that have larger physical sizes or specific designs. Capacitor types: different types of capacitors can offer high capacitance values. Electrolytic capacitors, such as aluminum electrolytic and tantalum capacitors, are known for their high capacitance. Supercapacitors, also known as ultracapacitors or double-layer capacitors, can provide extremely high capacitance values compared to traditional capacitors. High capacitance capacitors find applications in various industries and technologies. They are used in power electronics, energy storage systems, motor drives, audio equipment, telecommunications, automotive electronics, and many other electronic circuits. When selecting capacitors with high capacitance, it is essential to consider other factors such as voltage rating, ESR, temperature stability, and size, to ensure compatibility with the specific application requirements. High voltage rating in capacitors refers to their ability to withstand and operate reliably under higher applied voltages without breakdown or failure. Capacitors with high voltage ratings are designed to handle higher voltage levels, making them suitable for applications that require higher voltage capabilities. Here are some key points about high voltage ratings in capacitors. Definition: voltage rating specifies the maximum voltage that a capacitor can safely withstand without experiencing breakdown or insulation failure. It is typically expressed in volts, V, or kilovolts, kV. High voltage ratings indicate that a capacitor is designed to handle higher voltage levels. Voltage stress: capacitors are subjected to voltage stress during operation, which is the electrical potential difference applied across the capacitor terminals. High voltage ratings ensure that the capacitor can withstand the maximum voltage stress without insulation breakdown or other voltage-related issues. Safety and reliability: capacitors with high voltage ratings provide a higher safety margin, ensuring reliable operation under nominal or transient voltage conditions. They are less prone to voltage-induced failures, such as dielectric breakdown, which can lead to catastrophic capacitor failure or even damage to the surrounding circuitry. Voltage transients: high voltage-rated capacitors are capable of handling voltage transients or spikes that may occur in the system. Transients can result from power supply fluctuations, switching events, or electrical noise. Capacitors with high voltage ratings prevent excessive voltage stress during such events, maintaining stable operation and protecting sensitive components. Power electronics: high voltage rated capacitors are essential in power electronics applications, where high voltage levels are common. They are used in power supplies, inverters, motor drives, and other high-power systems that require energy storage, voltage regulation, or transient suppression. Electric vehicles: capacitors with high voltage ratings find applications in electric vehicles, EVs, and hybrid electric vehicles, HEVs. EVs and HEVs typically require capacitors capable of handling high voltage levels due to the high voltage battery systems and power electronics used in these vehicles. Voltage scaling. High voltage rated capacitors enable voltage scaling in electrical systems. By using capacitors with higher voltage ratings, system designers can increase the operating voltage of the circuit or device, allowing for more efficient power conversion and distribution. Size and construction. Capacitors with high voltage ratings often have larger physical sizes due to the increased insulation requirements. They may also employ specific dielectric materials and construction techniques to ensure reliable operation under high voltage conditions. When selecting capacitors with high voltage ratings, it is important to consider other factors such as capacitance value, ESR, temperature stability, and specific application requirements. Capacitors with the appropriate voltage rating should be chosen to ensure safe and reliable operation within the intended voltage range of the application. Stability and reliability are crucial characteristics in capacitors as they determine the capacitor's ability to maintain consistent performance over time and in various operating conditions. Here are some key points about stability and reliability in capacitors. Capacitance stability. Capacitance stability refers to the ability of a capacitor to maintain its specified capacitance value over time and under different operating conditions. Capacitors with good capacitance stability exhibit minimal changes in capacitance due to factors such as temperature variations, voltage stress, aging effects, and humidity. Stable capacitance ensures predictable and reliable performance in electronic circuits. Voltage stability. Voltage stability refers to the ability of a capacitor to maintain its specified capacitance value under varying applied voltages. Capacitors with high voltage stability exhibit minimal changes in capacitance with changes in voltage levels. This ensures consistent performance and accurate voltage regulation in applications that involve varying voltage conditions or voltage fluctuations. Temperature stability. Temperature stability refers to how well a capacitor maintains its specified capacitance value over a range of temperatures. Capacitors with good temperature stability exhibit minimal capacitance changes with temperature variations. Temperature stability is crucial in applications where the capacitor will be subjected to a wide temperature range, ensuring reliable performance across different environmental conditions. Aging stability. Aging stability refers to how well a capacitor retains its electrical properties and performance characteristics over an extended period of time. Capacitors with good aging stability exhibit minimal degradation or drift in capacitance, equivalent series resistance (ESR), or other electrical parameters. Capacitors with high aging stability have longer lifespans and can provide reliable operation over many years. Mechanical reliability. Mechanical reliability refers to the ability of a capacitor to withstand mechanical stress, such as vibrations, shocks, or thermal expansions/contractions, without experiencing physical damage or performance degradation. Capacitors with robust mechanical construction and materials exhibit high mechanical reliability, ensuring their longevity and resistance to physical stresses in demanding environments. Failure rate. The failure rate of capacitors is an important factor in assessing their reliability. Capacitors with low failure rates are less likely to experience premature failures or malfunctions. Manufacturers often provide reliability data, such as mean time between failures, MTBF, or failure rate percentages, to give an indication of a capacitor's expected reliability. Quality control. Reliable capacitors are manufactured with strict quality control processes in place. These processes include rigorous testing, quality assurance measures, and adherence to industry standards and specifications. Manufacturers that prioritize quality control and have a track record of producing reliable capacitors contribute to the overall stability and reliability of their products. Stability and reliability are critical considerations when selecting capacitors for applications that require consistent performance, long-term reliability, and durability. It is important to review manufacturer datasheets, reliability information, and application requirements to ensure that the chosen capacitors meet the desired stability and reliability criteria for the specific application. Safety features in capacitors are designed to prevent or mitigate potential hazards associated with their operation. These features help ensure the safe and reliable performance of capacitors in various applications. Here are some common safety features found in capacitors. Overvoltage protection. Overvoltage protection mechanisms prevent capacitors from experiencing excessive voltage levels that could lead to insulation breakdown or catastrophic failure. These mechanisms may include built-in voltage clamping devices, voltage-dependent resistors, VDRs, or self-healing properties that allow the capacitor to recover after an overvoltage event. Fail-safe design. Capacitors with fail-safe design features are designed to minimize the risk of hazardous conditions in the event of a failure. For example, some capacitors are designed to fail open, preventing the passage of current and minimizing the risk of short circuits or electrical faults. Pressure relief mechanisms. In certain capacitor types, such as electrolytic capacitors, pressure relief mechanisms are implemented to prevent the buildup of excessive internal pressure. These mechanisms ensure that if internal pressure exceeds safe limits, the capacitor will vent or release the pressure in a controlled manner, preventing rupture or explosion. Flame retardant materials. Capacitors designed for safety-critical applications may incorporate flame retardant materials in their construction. These materials help prevent or reduce the spread of fire in case of capacitor failure or exposure to high temperatures. Temperature protection. Capacitors may include temperature protection mechanisms to prevent overheating or damage due to excessive temperature conditions. These mechanisms can include thermal fuses, thermistors, or design features that improve heat dissipation and thermal management. Compliance with safety standards. Capacitor manufacturers ensure that their products comply with relevant safety standards and certifications. Compliance with standards such as UL, Underwriters Laboratories, IEC, International Electrotechnical Commission, and other regional safety regulations ensures that capacitors meet established safety requirements and have undergone rigorous testing. Markings and labeling. Capacitors often include clear invisible markings or labeling on their casings to indicate important safety information. This may include voltage ratings, temperature limits, safety warnings, polarity indications, and other relevant details to guide proper and safe usage. It is important to carefully consider the safety features and specifications of capacitors when selecting them for specific applications, especially in safety-critical systems or environments. Understanding the intended use, environmental conditions, and necessary safety certifications will help ensure the appropriate capacitor choice to maintain safe and reliable operation. Capacitors find application in a wide range of electronic and electrical systems across various industries. Here are some common application areas where capacitors are extensively used. Power supplies and energy storage. Capacitors are vital components in power supply circuits. They are used for energy storage, smoothing out voltage fluctuations, and providing instantaneous power during high-demand situations. Capacitors are also used in energy storage systems, such as batteries and supercapacitors. Motor start and run capacitors. Capacitors are widely used in electric motors to provide the necessary starting torque and smooth operation. Start capacitors provide the initial high torque during motor startup, while run capacitors help maintain a steady rotational speed. Signal coupling and decoupling. Capacitors are used for signal coupling and decoupling in electronic circuits. They allow the transfer of AC signals while blocking DC components. Capacitors help maintain signal integrity, remove noise, and improve the overall performance of audio and communication systems. Timing circuits. Capacitors are commonly used in timing circuits, such as oscillators and timing networks. They determine the frequency and period of waveforms, enabling precise timing and synchronization in applications like clocks, timers, and pulse generators. Filtering and frequency selection. Capacitors are used in filtering circuits to attenuate or remove specific frequency components from signals. They are employed in low-pass, high-pass, band-pass, and band-stop filters. Capacitors play a vital role in audio equalizers, active crossovers, and radio frequency (RF) filters. Voltage regulation. Capacitors are used in voltage regulator circuits to stabilize and regulate the voltage levels. They help smoothen the output voltage, compensate for load changes, and improve the transient response of voltage regulators. Power factor correction (PFC) capacitors are utilized in power factor correction circuits to improve the power factor of electrical systems. They help minimize reactive power, improve energy efficiency, and reduce power losses in industrial and commercial applications. Coupling and decoupling in integrated circuits (ICs) capacitors are essential in IC packaging and board-level designs. They provide coupling and decoupling functions to stabilize the power supply voltage and reduce noise interference in ICs. Lighting capacitors are used in lighting systems for power factor correction, energy storage in fluorescent lamps, and as a component of electronic ballasts in fluorescent and high-intensity discharge (HID) lamps. Automotive electronics capacitors are employed in various automotive applications, including engine control units (ECUs), airbag systems, ignition systems, entertainment systems, and powertrain control modules. They contribute to reliable operation and stable performance in demanding automotive environments. Audio systems capacitors are used in audio systems for coupling, decoupling, filtering, and tone control. They influence the frequency response, impedance matching, and overall sound quality in amplifiers, speakers, microphones, and audio recording equipment. Consumer electronics capacitors are ubiquitous in consumer electronics, including smartphones, televisions, computers, home appliances, and audio-video equipment. They play a critical role in power supply circuits, signal processing, filtering, and energy storage. These are just a few examples of the wide-ranging application areas of capacitors. Capacitors are versatile components used in almost every electronic device and electrical system, providing essential functions in power management, signal processing, timing, filtering, and energy storage. The specific capacitor requirements vary depending on the application and the choice of capacitor type, voltage rating, capacitance, temperature stability, and other specifications should be carefully considered to ensure optimal performance in each application. It is important to note that tantalum polymer capacitors, like other tantalum capacitors, are polarized and must be connected in the correct orientation to avoid damage. Additionally, while tantalum polymer capacitors offer numerous advantages, they are typically more expensive than some other capacitor types. Careful consideration of the specific requirements, performance characteristics, and cost constraints of the application is important when selecting tantalum polymer capacitors.